So I was very pleased to see that it was a crappy day outside today because it means the opportunity cost of your time is pretty low. So whatever I do today, it's got to be better than your outside option. So today I want to talk a little about machine learning for science. And specifically, most of what I'm going to focus on is machine learning for behavioral science. And I don't know why I can't get this to work. Oh, we'll switch here. There we go. That's why. So, but before doing that, let me just give you a sense of the overall space of ML for science as it stands, since some of you may not be familiar with this branch of work. Perhaps the thing that you're most familiar with would be protein folding. So if you look at protein folding, there's an amino acid sequence, and the question there is, what will the folded version of the amino acid sequence look like? That matters because only the exposed bits can bind to things, so the protein's functionality depends on how it has folded, i.e. what's on the outside. This is a hard problem, but we've had a lot of progress. This is up to 2020. We've had more progress since 2020. Just as this is from an ad for AlphaFold, but you've probably all seen this AlphaFold ad. Dramatic progress in the world of protein folding. This is an old science problem where we've had big computational progress. It's not the only one. There's been huge work in material sciences where, much like we tried to predict protein targets, protein folded structures, there people have tried to discover materials with certain properties that you were able to do. And this is huge breakthroughs. We've seen breakthroughs in math, for example. This is very recent. And all of these things that are bubbling, I think, fit under a particular way of viewing the world, which is they all have a property where we've got a correct theory of some form. So we know the rules of organic chemistry. We know the rules of quantum mechanics. We know the rules of deduction underneath math. So for all three of these things, we know the theory, but implementing the theory in any practical sense is very hard. It's very hard to compute the theory all the way through and actually compute the protein. So the way I view this part of ML for science is that it takes correct theories, correct enough theories, but that are very hard to implement and finds tractable versions of them. And it's just shocking that despite all of our efforts to optimize and find approximations, ML algorithms appear to be able to find much better approximations, faster implemented, so on. So that's one branch of ML for science. And I think things like material science, math, biology all fit this. They have advantages. They're able to use simulated data from theory because you've got the true theory. You can actually start simulating data to train it. And ML finds approximators. This is a pretty active area. I want to talk about a different area where ML is useful. It's closer to the work I do in behavioral science, where I don't think anybody anywhere wakes up and says, you know, where we have correct theories are theories of human behavior. So I think it's fair to say we have, I won't say incorrect because I have colleagues. Let's say we've got incomplete theories of human behavior. Here the goal isn't to approximate this incomplete theory. It's in fact to improve this theory. This is a very different approach. It's a very different structure. These two things can all look like ML for science, but they will just feel very different, and they will require different tools be built. Now, things that fit here is behavioral science. But in fact, other problems, such as weather, have this property. Because we certainly don't have, well, you could say we have a theory of weather at some molecular level. We don't actually have a theory at the measurement frame that is correct. We're actually looking for a theory at the measurement frame that's correct. Medicine is another extremely promising application. And here the goal is to create tools. It requires real data. We use supervised learning to get better fit of that data than the theory might give us. But then we need tools to be able to extract conceptual insights from that. In the former one, we're happy to just know that, wow, we can do protein folding better. But here, if the goal is to improve the theory, it's not enough to just sort of get a predictive model. We need to get something conceptual out of there. And so these two branches of kinds of ML for science, for me, it was helpful to see the distinction. Everything I'm going to talk about is in the second category. And I will give you two distinct examples in that second category where they're sort of empirical examples, and they have an important distinction. They both involve human behavior, but that distinction means there are two very different tools needed. So for the first one, I'm going to talk about a very concrete problem. So we'll start very, very applied. Every year in the United States, there are about 12 million arrests. This is if you pause for a minute, you'll realize how big of a number this is. Shortly after arrest, the judge has to make a pretty important decision. Will this person who's just been arrested spend their time between now and trial at home, or will they spend it in jail? This is a hugely consequential decision because the average stay in jail is about 2 to 3 months. So if the judge decides, oh, you need to wait for trial in jail, your life is pretty much like completely over. You've just lost your job, you've lost everything. But the judge is not trying to decide your guilt. By law, that's not their goal. They can't. It's a quick trial. They're trying to decide what risks do you pose to society during this intervening period. And their goal is to jail those at high risk. So this work we did before, now what I'm about to tell you is just a setup to something. This work we did before asked the question, are judges jailing the right people? In other words, if you think of this as a pure risk prediction problem, there's a supervised learning element here, and the judge is acting as a supervised learner. Given the inputs I see of the person, make a prediction. So in that paper from 6 years ago, we asked, can algorithms improve judicial decision making? I'm not going to go into the details of it, except to just point out that you find huge effects. So you tend to find you can keep crime rates fixed relative to what judges do and reduce the jail populations by 40%. The misranking is so bad that you can actually just release a ton of people as long as you rank the remainder correctly. Or you could keep jail populations fixed and reduce crime by 24%. There's a bunch of subtle issues here which I'm not going to go through, including issues like racial bias and equity, and that's what the body of work there is dealt with. But what I want to talk about today is the scientific part. Assume for a minute judges are doing a bad job, just for the purposes of this talk. Well, as a behavioral scientist, part of what you want to ask is, wait, why can algorithms improve so much? What are judges getting wrong? What's going on in their psychology that is leading them to such gross errors, assuming you believe those numbers? How do we go about answering these questions? Well, typically, the way that scientists of all ilk would answer this question is that they would generate a hypothesis, and then they would test it. And it's just worth noting how hilariously asymmetric this whole process is. For testing, we have this huge array of methods that span the spectrum from structural modeling to randomized control trials to lab experiments. We have a lot of methods. We've come up with a lot of them. But for this bit, I think where do we get our hypotheses? It's our intuition. And so while this bit is meticulous, this generation bit is haphazard. This almost feels like a pre-scientific activity. This is inspiration. It's creativity. But there's something inconsistent here. What is a good hypothesis? Well, a good hypothesis is something like, at least has some properties of, I noticed a pattern in the world that we have not hitherto noticed, and maybe we should investigate whether that pattern is causal. But if that's what it is, well, if we just agreed in this paper judges aren't great at pattern detection, well, I'm just a scientist. I'm just a person. Is it possible I'm not perfect at pattern detection? Is it possible there are other patterns to be detected? That is, if we're making the conceit that supervised learning algorithms can help judges, shouldn't we ask, can't supervised learning algorithms help me? Might it notice patterns in the data? But what patterns do we care about? In the original paper, it was patterns about defendant behavior. So the camera, the algorithm, was predicting the defendant's risk, and we're comparing it to the judge's prediction of risk. But I'm not looking at the defendant. I'm looking at the judge. So what if we turned the camera on the judge and built a purely predictive model of the judge? Are there things in that predictive model that might be hypotheses I'd overlooked? So let's do that. So we build a predictive model of the judge, and we can ask which factors predict judge decision. What I'm going to do now is not the meat of the paper. It's just something to get us going. So this is going to be the dumbest exercise. We built a supervised learning algorithm of the judge using a bunch of data, and all we did is some very crude variable importance type measure. So in that crude measure, I'm going to show you the 5 variables that are the most important. So the first most variable is current charge, drug crime. In other words, is the current thing that the person has been arrested for a drug crime? That's the 5th most important variable. The 4th, oh, it's like interesting. It's current charge felony crime. The 3rd, oh, so you're starting to see a pattern here. 2nd, oh, it's really, okay. Now you see the things judges really care about. It's the current charges. In fact, these 2 through 5 have led some legal scholars to talk about how there is a current charge bias on the part of judges. Kind of makes you curious what number 1 is, and it made us think, oh, I wonder which current charge is missing from this list. People usually are like, oh, maybe it's murder, maybe it's something. In fact, it turns out the number 1 most important factor for predicting the judge decision is the current charge of having the wrong face. So the pixels in the mugshot are extremely predictive of who the judge will jail. And this 1 through 5 list is very odd. It's not 1 through 5. If you built a new predictor where I deleted all the rest of the data and I just predict who the judge will release using just the mugshot, that explains about half of the predictable variation. So it's not 1 through 5. It's like 1 captures half of the variation, and all the other things are capturing the remaining half. So the mugshot is playing an insanely large effect in what the judge is doing. Of course, this by itself is not a great hypothesis. It's a weird fact. It's a surprise. It's a disturbing fact. But it's not what we'd call a hypothesis. And it's not what we'd call a hypothesis for a couple of reasons. The first reason is, after you see the role that the face plays, you can ex post be like, well, of course. Because in the pixels of the mugshot, there are things that we already know should matter that the pixels might be capturing. For example, race, skin color, gender, age. That's not going to surprise us. So the first thing we have to do, which I won't go through in detail here, is we have to just check that those things, are those what the algorithm is rediscovering? But it's not just that. Like, while mugshots are new to me, mugshots are maybe new to you, psychologists have been studying faces for a long time. And they have a bunch of hypotheses about what in the face should matter. So if we're just rediscovering what psychologists knew, that's interesting, that's just from a mugshot data set, but it's not a new hypothesis. Finally, you might say, yeah, maybe it's not in the scientific literature, but honestly, if I looked at those mugshots, I'd see it myself. So what we do is we quantify all these in our mugshots, and then we do another exercise where we have people look at the mugshots and make their best guess of whether the judge will jail or detain this person. They're given incentives to get it right, they learn, and then they do that game. So now between these 3, what do we have? We have our best attempt at the collective human understanding of what's in the mugshot. The first 2 are explicit, the third is implicit, but it's at least our best human guesses. We can now quantify those mugshot by mugshot, and we can ask how much of the predictive power of the algorithm comes from these things. 2 things emerge when you do that. The first thing is that the algorithm, this I found surprising, I mean, I truly found this surprising, is that the algorithm rediscovers all of these. These independently have no more signal above and beyond what's in the algorithm, which is striking to me. Because this is like stuff we knew. It's like context knowledge. But it also is the case that collectively they explain little of what the algorithm has found. So about 15 to 18% of the predictive signal in the face is explained by these things, which suggests there's a lot. But of course, this just says there's new information. But a hypothesis is more. It's an interpretable, meaningful, conceptual insight. So what we now need is a way to communicate with the algorithm. So let me try to articulate what is the algorithmic communication problem. On the left-hand side, if I anthropomorphize a bit, the algorithm knows the m of x function. It's from pixels to some prediction. On the right, we sit. What we know is a bunch of functions from pixels to something, which are features. Handsome, whatever, whatever. Those are all features. They're all pixel functions. We know them. But, and this is the key, the space of functions is not formally describable here. I can't tell you this is a mathematical description of human interpretable pixel functions. What does that mean? I wouldn't even know how to write that set. It's because we know implicitly when we see a mugshot how to calculate attractiveness, but we don't know the function for it, nor do we know the set of input. What that means is communication here is not mathematically just an activity of projecting m of x onto h. Even though I can say that's all I'm trying to do, algorithmically I can't do it. I don't have access to h. I only have a procedure called the people who can then tell me individual, but that's it. I don't have h. So what we need is a communication procedure where the algorithm and the human can talk continuing my anthropomorphizing, and they can output an H out of that, which a human can understand. Great. So this approach is going to be algorithm discovers human names, so to speak, or names some subset of the discovery. So what does that communication predictor look like? Well, one common approach would be to take my black box algorithm and do some sort of gradient method. So for those of you who are not familiar with it, we take a COMNET, for example. What a gradient method does is, so a COMNET here is taking the pixel, it's creating a 3-channel matrix, it's going to turn these pixel tensors, going to go through, you get the prediction. You can zoom in on any of one of the inputs, let's call it the red input right here. Change that 194, that's the gradient part, see how the prediction changes, and isolate pixels where the changes in those pixels lead to the biggest change in prediction. The result of all that activity is now you are able to identify in the image, in any given image, which pixels are doing the work. So that's the essence of all this. I will do this, which is helpful. Basically, what's happening here is there's image space. These are each point here is a combination of pixels. There's some contour map of the prediction function. All we're doing here is picking a specific face here, forming the gradient, and then we're going to visualize that gradient into a saliency map. And let's do that. So this is an example. This is a mugshot. If you do that for our predictor, you get this, which is a very insightful saliency map that tells you the algorithm is looking at the face. It really doesn't work. It doesn't work here for kind of obvious reasons. Face features are composite functions. There is no single point in the face that tells you, oh, if you look here, you can see if someone is attractive. For some reason, I always use that example, and then at this point in the talk, I become very self-conscious that people are looking at my face. This feels like I should find a different thing. They're not localized to one specific place in the face. Great. But that's OK. We know that people understand through comprehension. So why are we trying to localize? Why don't we just follow the gradient? Why don't we take that image and simply just follow the gradient and change the face until we get a nearby new face? Great. So that's what we're going to do. When we do that, we get this monstrosity. This is also really bad. What's going on here? Well, what's going on here is actually transparent in this image that I put forward. What's going on here is that I said, oh, let me just follow this gradient. I calculated it, and I'll just follow it, and I'll have this morph face. But this picture is a lie. It's a lie because you'll notice this is image space. Faces are a tiny, tiny sliver of this space. So when I follow the gradient, I end up off of the manifold, the submanifold of faces. So what this requires is a different kind of tool, and it requires us to stop leaving the manifold, and it requires us to combine the supervised learning model with some generative model. That is, we need a model of the submanifold, and we need to be able to project the supervised learner into that submanifold and follow the gradient in that submanifold. And that's what we do, just in the spirit of time. I will go through this fairly quickly. We build a mugshot GAN, where we take all our mugshots and we create a model that can produce synthetic mugshots. It actually works pretty well. Here are 4 images. It turns out 2 of these are real, and 2 of these are fake. In fact, the previous guy I told you was not a real. None of the photos here, except 2 here, are real. The previous guy I showed you is actually a synthetic mugshot. And you get very realistic synthetic mugshots. I never remember which 2 are real, which 2 are fake, so I'm sorry I can't answer that question. And now we're going to project the predictor into the subspace and follow the gradient. So how are we going to do it? Well, we're going to have people communicate. That way we know that this is a reliable, repeatable procedure. It's not going to be us looking at these. So we're going to take the judge predictor, combine it with the GAN. We have the morphing tool. Here you can see what the morphing tool looks like. We start in the middle. We morph to the left to increase the tension probability, morph to the right to decrease the tension probability. And we get this. We take the edges of this and we show them to people. So this is another pair. And then people will look at these. They'll do this again and again. And they're going to play a little game They're going to say, here's pairs. Why don't you guess which one is the higher detention probability? Then I'm going to give you some feedback, so you get a chance to learn. You get incentives to get it right, and you play this game. You get pretty good at it. And at the end, we ask them, hey, what were you looking for in trying to do well at this game? So, do they actually do well? They actually do pretty well, and at the actual guessing task, well enough. And then you ask, do they all articulate something together that's somewhat reasonable? So for this one, here's the word cloud of what they say. And if you stare at it, you can see there is actually a center of mass that pops out. With a little bit of tokenization, it really pops out. About 40% of people say, oh, well-groomed, or some synonym of well-groomed. Of course, that well-groomed turns out to explain a huge fraction of the predictable variation, about 8 to 9%. It's much more important than race, for example, in this. But there's more where this came from. So now, since well-groomed only explains a fraction of it, we can now do exactly what we just did, but morph again, but orthogonalizing with respect to well-groomed. This turns out to introduce a pretty hard technical challenge that I can confidently say we did nothing but hack our way around. So I'll summarize this technical challenge for you, because we definitely do not have a solution to this. The challenge is, when I said we're going to orthogonalize against well-groomed, well, technically, in the generative space, I don't have well-groomed. What do I have? I have a predictor of well-groomed. And any predictor of well-groomed has some error. But because the original predictor is correlated with well-groomed, as I follow what I think is the orthogonal component, I am actually following the prediction error in well-groomed, and I'm actually following well-groomed. So it's quite hard to do this without just getting back on the well-groomed gradient, because that was the first gradient that you got. So it's very hard to do this. I can tell you how we hacked our way around it, but it's fine. This was one of those things that I really don't know. There must be a nice solution. We don't have a great solution. We have something that works, but not something that's general. When you do this, you then do the whole game with subjects again with these pairs. You get a second feature, also interesting. This second feature pops out much more obviously than the first one did. So it's weird that the second one seems to be more first order than the first one. And you can see it in these photos. And when you ask people what you get, in fact, it turns out that it's something like full-faced, or heavy-faced, or fat-faced. But interestingly, unlike well-groomed, where I'm sure you all had an intuition that the well-groomed person is more likely to be released, I'm curious whether people have an intuition whether the fat-faced person is more likely to be released or jailed. It's not, when I do this with audiences, I get about 50-50. But in fact, being full-faced is strongly predictive, and is predictive in the direction that full-faced people, the man on the right, not the man, the made-up person on the right, is much more likely to be released than the person on the left. So I won't keep iterating. I'll just point out this is just a proof of concept. But now that we've got these hypotheses, though, we could go back and look, do these hypotheses bear any resemblance in the original data? So we can take the algorithm out of it. We can just have images coded for well-groomed and full-faced. And when you do that and you ask how predictive is it of judge decisions, extremely predictive. So the magnitudes, just so you get a sense, between a well-groomed and non-well-groomed person, it's about 28.7% detention rates, which is on the same scale as having committed an extremely violent crime. So you can shave and commit a violent crime and be not too far off. Similarly, full face is about 30%. So these effects are huge. They are far bigger than, for example, the effects of race or skin color. This is, the only things that come close to this are the effects of gender and violent crimes. So these two features, judges play a lot. Are these new? Well, you can go back to public defenders. You can ask them to list features. Some public defenders list well-groomed. None of them list fat-faced, full-faced. They even work causally in lab experiments. You can have people decide who to jail based on the entire thing, and you can give some people randomly manipulated photos with photos along these dimensions, and they affect things. It's also the case that these features, you may be curious, don't actually predict risk. So this is not some, oh, we found facial features that predict actual risk. These almost certainly appear to be biased by the judge. But this is not a paper about well-groomed or full-face. It's not even a paper about judges. I hope you see it's a paper about a new way to study people that really is just a way to generate hypotheses, not just from images. It's really from any high-dimensional input. And to me, this is the first of the two things, where in the mugshot case, what we have is a context where the algorithm knows something. The human has understanding that's implicit, and we need something like morphing, and maybe there are other techniques that allow communication, so that what we really have is an intuitive theory, is the first application. And a lot of social science is about intuitive theories, the theories that we don't have written down formally. And the goal here is a novel hypothesis. But what if we have a formal theory? There are many theories in social science where we do have formal theories. Some of them are used quite widely in computing. For example, expected utility theory plays a pretty big role in many parts of computer science. So what if we had a formal theory? Is there something else we could do that would look very different? So to do that, let's just consider how do we improve theories, formal theories, currently. And so here I want to start with expected utility theory. Expected utility theory, just to remind you, is a set of axioms that tell us how people choose when making decisions under risk. And those axioms imply various representations of choice. You're probably most familiar with sum of probability times utility. And that is sort of the workhorse. When expected utility theory was first built, there's a famous paradox by Allais. It's called the paradox, where it's actually a very simple thing. He just said, oh, this is nice. These axioms are really interesting. Let me just show you something. If I had people choose between these two lotteries, $1 million or this lottery B, where you get 89% chance of 1 million, so that's what you had before. Ooh, now you have a 10% chance of 5 million, but you have a 1% chance of nothing. So I have people choose these. He said, intuitively, I think you can imagine most people are going to pick this. It's not hard to see why. They're like, why am I going to risk losing the million? It's crazy. Let's not get greedy here. Then he said, great, that all makes sense. Let's show people lottery C. You have 89% chance of nothing and an 11% chance of 1 million. Or lottery D, 90% chance of nothing or a 10% chance of 5 million. Now think about what you choose. I think almost all of you would clearly choose lottery D. It's like, what's 1%? It's long odds anyway. Might as well go for the $5 million. And Allais simply pointed out, algebraically speaking, these two choices are inconsistent with the independence axiom. And the reason for that is you can actually rewrite lottery A and B as combinations back of lottery C and D by simply, C and D as combinations of A and B by simply adding things back. And so this is what we're going to call an anomaly. It's sort of a minimum presentation of a very simple example which shows the theory must be wrong somewhere. Because it's just, and these examples are powerful. It is not just Allais. If you look at the history of expected utility theory, we had Allais, we had something called the common ratio effect. Kahneman and Tversky, whom many of you may be familiar with, did many such anomalies, and together that led to prospect theory. Prospect theory, of course, led to more anomalies, and that led to new theories of decision making. And this is an active area where people are still kind of producing new anomalies and using those anomalies to generate insights to produce better models of decision making under uncertainty. The anomaly is the core object for the evolution of these sciences. But it's also true in many other places where we start to go in game theory, for example. We start with a model, anomaly, 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 new theory. So that's how we went from Nash equilibrium to subgame perfect equilibrium to Bayesian subgame perfect equilibrium. We said, look, in this game, Nash doesn't make sense. Oh, that's true. That is weird. That's weird. It doesn't make sense in that game. Let's keep going. That's also what happened in finance, for those of you who are familiar with it. We had CAP-M, concept. You can actually go through theories and just do the history of science, and you'll realize anomalies play an extremely large role in science. So how do we typically find anomalies? Well, here's a parody of the current anomaly generation paradigm. There's somebody smart, like Allais, who looked at the world. Allais looked at the theory we have, expected utility theory. He contrasted them, and he said, something seems wrong here. And he carefully crafted an anomaly that violates expected utility theory, but he believes will be true in the world, where he's basically using his understanding of the world and contrasting it with the theory to find this minimal example. Now, it's all human. But of course, you'll notice observing patterns, as you saw in the Faces paper, is kind of the ideal thing that an ML model could do. So perhaps, given that, we could actually automate the entire pipeline. What do I mean by that? Suppose we wanted to take this whole bit and just have it produce anomalies. What does it need? It needs some data on behavior to build the first supervised learning bit. Then it needs a formal description of the theory. And it needs this contrastive function. It needs to be able to contrast whatever signal is in the ML model with the theory. And then it needs to be able to produce this minimal object. So to do this, this is the thing we're trying to build. Take a theory, take a predictor, contrast, build anomalies. Turns out that formalizing what a theory is harder than we thought it would be, because we're not just formalizing one theory. It's sort of any theory, and different theories come in very different form factors. It also turned out it's harder to formalize what an anomaly is, simply because we've described individual ones for EU, but if you think of the breadth of statistics, anomalies like LA don't really have any role specifically in and of themselves in many of our procedures. This isn't a p-test, a p-value. It's not a t-test statistic. It's not a goodness of fit measure. What is the LA paradox? I mean, if you went and collected data on it, you could do something on the numbers you got, but the object itself, it's not clear what it is. So part of what we had to do is to formalize what a theory is, formalize what anomalies are in a way that also encompasses the statistical objects that is machine learning with the logical and theoretical objects that are theories and anomalies. I'll skip that because I've got like 5 minutes left. What I want to do is to then say, once we have those formalized, the interesting bit is, what does it look like to automatically generate an anomaly? And this is the bit that in the Faces paper, because we didn't have the theory in a formal way, we just had to resort to some communication. But here we've got the theory in a box. We can actually make procedure calls to it. And it turns out that an anomaly is an equilibrium in a game. Let me explain what I mean. So if LA were to produce a pair of menus, or 3 menus, or 4 menus, and say, I think people will choose A here, B here, A here, C here, that's a proposal. The theory now gets to respond to that proposal and say, oh, I can rationalize that. People have this utility function. People have these preferences. So there's a game here, which is the proposer picks a set of inputs. The theory gets to rationalize those inputs. That is, after all, what theories are. They're incredibly flexible. We haven't said people have to have these preferences. We said any preferences that fit these axioms are fine. So the theory gets to move second. So what's happening here is that the proposer picks the inputs, and the theory tries to pick its rationalization, and then we see what actually happens on those inputs, and if the theory can't match what actually happened, that's the anomaly. And we're trying to find the smallest such object. So interesting anomaly search is just max-min. Falsifier proposes, theory explains. And notice none of this is in the data set that we originally had. This is completely out of distribution at this point. So anomaly generation is now converted into max-min, which then means to actually find anomalies, we can use these interesting insights people have had on these type of problems. For example, when we do poisoning attacks for supervised learning, this is actually poisoning attacks on the theory. And that machinery works extremely well. You probably all have seen this, but I'll skip this. Poisoning attacks are where we take a supervised learning algorithm and say, you think this is a panda, I add this. Look, it still looks like a panda, but you think it's a gibbon. So these are attempts to basically, they're like the same max-min. You're trying to get the algorithm to commit. So we can adapt recent breakthroughs in convex, non-concave optimization to sort of solve this problem. And what you find is that that actually produces, in this case, anomalies. So when we take real data on actual choices, just some sample of choices, build a predictive model of how people choose in lotteries, and then put it through this procedure where you contrast expected utility theory with these choices, what you get is you get, I'll skip this. What you turn out is you get these discovered anomalies that fall into these 5 categories. We've made up these 5 categories. And it finds a lot of anomalies. But what's striking is all the known anomalies in the literature actually just fall into these 2 bins. And so it's just like with Faces, it has an interesting property. It rediscovers the known anomalies that scientists have kind of built up over time. But it finds a whole host of new ones. Of course, these are logical suggestions. We don't have data on it. These don't appear in our data set. So now we can go collect data on these. And when you go collect on these, you tend to find that the anomalies, each of these columns is an anomaly in each of the bins we discovered. And you collect what are the rate of violations. It turns out the rate of violations are approximately the same level as the LA paradox, which is amongst the highest violation space. So in the interest of time, let me, oh my goodness, that is an incredible, incredible level of typo. Who knows what the hell I was doing. So let me conclude on this. So what you've now seen, I hope, is that there are a couple, my God, was I drunk? Just amazing. I blame my keyboard. So there are two ways in this branch of ML for science that I hope you've seen. One is implicit theories, for which what we're trying to do is generate hypotheses. Those will be qualitative in nature. The other is formal explicit theories, where we're actually able, without even humans in the loop, to automatically generate small instances that you can look at and say, oh my God, that must be where my theory is. Or at least you can test to see if that's where your theory is going wrong. And I think for me, what I'm excited about is there's a lot more to be done in this branch, simply because unlike in the sort of the first branch, where the work is about largely implementing our theories for purposes of doing things with them, here I feel like the vista is quite wide open. Our theories in many of these domains I've listed last time are not particularly good, which means our chance to accelerate discovery is quite high in this area. So let me stop there, and if there are questions, we'll move there. Thank you.
So we've got time for a couple quick questions. So any questions for Sendhil?
Oh, look, there are no typos. I don't know what I was thinking.
Please feel free to come up to the mic here on either side.
I'll answer that. So for your judge example, I mean, how much do these things like full faceness, grooming, are they cultural norms that could vary across different legal systems?
I would be surprised if some of them weren't. Here we have judges from one jurisdiction, and so we just know it for that jurisdiction. The extent to which it generalizes, it's just not known. We just don't know. Yeah.
Just at a high level, I was wondering, how do you formulate what theories are? Like, how do you encode this generation of theories?
Yeah, so in the middle one, implicit, we punt, that you know. On the third one, it turns out that if you were just trying to formalize what a theory is, it actually works to not look at the representation or implementation of a theory, but instead to just treat the theory as a black box and say any black box that has follows these axioms is a theory. The axioms are quite intuitive. The most important axiom, what separates an ML black box from a theory? An ML black box is one where as you get more data, as with many non-parametric things, it can keep adapting. Theories do not adapt. Theories commit. Theories have a structure, so they commit. So there is their sample after which they are not. They can be fitting parameters in it, but the broad structure they're sitting in. And so once you formalize that, it turns out pretty much every theory we could do fits those conditions because they're pretty intuitive. And then you have a representation result that says for every theory that satisfies these, there's a universal representation. And so everything we do is operating off of that universal representation. That universal representation is pretty easy to compute. So if you gave me a theory in one representation, we can compute that. And then this thing just can work off of that universal representation. Yeah. Great. Yeah.
This idea of the anomaly generator is quite interesting. I'm wondering if you're thinking about using this as a way to explore the space of theories as well, some sort of a closed loop.
Yeah. Yeah, so one of the areas that I think you're getting at, which is what we're thinking about now, and where I'd love to see more people work, is if you could go from anomaly back to automatic theory improvement, that would be very interesting. And you can see then, to your point, you can just start doing this in a loop. That's what we're trying to do now. And I say try because let me just articulate what makes that problem hard. What makes that problem hard is to be able to do this automatically. You don't need to know what is one formal theory. You need to have modeled a space of theories that you're now searching in. And that's just a little harder than you would think. And so the reason it's a little harder than you would think is that in people who have done that sort of stuff, I think they've equated theories with single equations. But a theory is not a single equation. Like take expected utility theory. It's not a single equation. We don't all have one utility function. It's a collection of possibilities, which we've chosen to represent as sum of p times u of x. But given any data, I can pick from that huge space of possibilities. So you're actually not fitting a new equation. That's where the optical illusion comes from. In some areas, you can just say, look, I found a better equation. But a theory is not one equation. A theory is a collection of modelable possibilities. So the hard part is in modeling that set, so this set that we're going to search over. And so that's the technical challenge. But I'm confident somebody's going to crack that, and then we'll be able to get some loops going there.
Great, let's thank Sendhil again, and we can continue the discussion over lunch.
Thank you.